Hi, hello, this is your Lucky sir. We'll go with NCRT VSCPR theory. We don't want to miss any single point, that's why we are going with the NCRT textbook. Valential electron pair repulsion theory. Wherever it is required, I explain you the few points. Otherwise, we'll just read, check out all the important points for IIT as well as NEET. As already explained, Lewis concept is unable to explain the shapes of molecules. This theory provides a simple procedure to predict the shapes of covalent molecules. Sedgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pairs in the valence shell of the atoms. That's why the theory, valence shell electron pair repulsion, VSEPR. It was further developed by Nyholm and Gillespie. Scientist names are not required. Of course, I salute to them, right? The main postulates of Vesper theory are as follows. The shape of a molecule depends upon the number of valence shell electron pairs, bonded or non-bonded, around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. All electrons are negatively charged, so repulsions will be there. These pairs of electrons tend to occupy such positions in space that minimize repulsions and thus maximize the stability, or is a distance between them. So minimum repulsions, maximum stability. This is our major idea. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at a maximum distance from one another. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. Question cannot be framed on this statement. A multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of a multiple bond are treated as a single super pair. Single super pair, right? Where two or more resonance structures can represent a molecule, the Vesper model is applicable to any such structure. The repulsive interaction of electron pairs decrease in the order of lone pair, maximum, then lone pair, bond pair, least is bond pair, bond pair. Bond pair repulsions will be minimum. It is like you and your brother. If you are both are at home, you will be always fighting for remote, for chocolates and everything. If one of you are in hostel, then the repulsions are minimum. You show a lot of affection, right? Same thing. Nyholm and Gillespie refined the Vesper model by explaining the important difference between the lone pairs and bonding pairs of electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between the two atoms. Lone pair means like you and your brother at home. Bond pair means you and your brother, you are in USA and your brother in Australia. As a result, the lone pair of electrons in a molecule occupy more space as compared to the bonding pairs of electrons. This results in greater repulsions between the lone pairs of electrons as compared to the lone pair bond pair and bond pair repulsions. So when both of you are at home, you will fight always. If you are in different places, you show a lot of affection, right? Distance increases affection, but don't keep people too away so that they can forget you. This is life philosophy. Okay, these repulsion affects results in deviation from idealized shapes and alternations in bond angles in molecules. That means some changes will be there. For example, 3 electron pairs are there. It should be trigonal planar, but if one of them is lone pair, it will change. For the prediction of geometrical shapes of molecules with the help of Vesper theory, it is convenient to divide molecules into two categories, as molecules in which the central atom has no lone pair and molecules in which the central atom has one or more lone pairs. Table 4.6, page 110 shows the arrangement of electron pairs about a central atom A without any lone pairs and geometries of some molecules ions of the type AB. Table 4.7, page 111 shows shapes of some simple molecules and ions in which the central atom has one or more lone pairs. We'll discuss in detail now. Table 4.8, page 112 explains the reasons for the distortions in the geometry of the molecule. As depicted, In table 4.6, in the compounds of AB2, AB3, AB4, AB5 and AB6, the arrangement of electron pairs and the B atoms around the central atom A are linear, trigonal planar, tetrahedral, trigonal bipyramidal and octahedral. 2, 3 electron pairs, 4 electron pairs, 5 electron pairs and 6 electron pairs. Such arrangement can be seen in the molecules like BF3, it is AB3 type, CH4, AB4, PCl5, AB5 as depicted by below their ball and stick models. See, this is beryllium, these two are chlorines, this is boron, these are fluorine atoms, this is carbon, these are hydrogen atoms, this is phosphorus, all these are chlorine atoms. These are in the plane and one is above the plane, one is below the plane. The shapes of molecules in which central atom has no lone pair, this is the case. The Vesper theory is able to predict geometry of a large number of molecules, especially the compounds of p-block elements, accurately. It is also quite successful in determining the geometry quite accurately even when the energy difference between the possible structures is very, very small. The theoretical basis of the Vesper theory regarding the effects of electron pair repulsions on molecular shapes is not clear and continues to be a subject of doubt and discussion. Okay, so for our questions purpose, you can very comfortably go with this. See, let us say this is teacher, these are the two students, they are writing exam, so this is the best way. On a bench, teacher is sitting in the middle, two students are sitting here, no copying, fine. So if 3 students are there, teacher is here, student 1, student 2, student 3. If 4 students are there, better. One student is going on to the fan, okay, he is sitting on the fan is not moving, okay, and teacher is sitting on a stool, on chair, 3 students are sitting like this. So that shape is called tetrahedral. It is trigonal planar, 2 linear, 5 trigonal bipyramidal, 6 is octahedral. Okay, examples are mentioned here, BeCl2, HgCl2. If you want, you can add more CO2, C2H2 type, BF3, BCl3, AlCl3, CH4, NH4 plus, PCl5 and here SF6. These are the best examples where there are no lone pairs. If lone pairs are there, A central atom, B bonded atoms, E is lone pair. 2 bond pairs, 1 lone pair. Now this is not coming into the shape, it is a lone pair. So this is the shape and this shape is bent shape, SO2, O3, or you can take even SnCl2 also. AB3E, where 3 bond pairs and 1 lone pair. Trigonal pyramidal, ammonia is the best example. NF3 also you can take. PH3, PF3, all that you can take. If 2 lone pairs are there, that is bent like water shape, H2S also you can take. AB4E, 4 bond pairs, 1 lone pair, this is the lone pair, so this is the remaining shape, this shape is seesaw. Seesaw, school, you will be playing, you are sitting here, your friend is sitting here, if you are Motu, it will go down, if your friend is Motu, it will go down, otherwise you can push some force and you can play with this, that is seesaw, yes, exactly seesaw. AB3E2, T shape, you see this is T shape, it is lone pair, it is lone pair, so this is T. CLF3 is the example. And 5 and here one more you can add, AB2E3, 2, 3, XeF2 you can shape, linear shape, XeF2 example. AB5E, 5 bond pairs, 1 lone pair, this is the geometry, 1 square, 1 pyramid, square pyramid. AB4E2 only square planar. Examples, these examples we read so many times. And here the reasons are given is AB to E, if 4 bond pairs and 1 lone pair is present. Okay, number of bonding pairs, it's a mistake. 2 and 1. Theoretically, the shape could have been triangular planar, but actually it is found to be bent or V-shaped. The reason for being the lone pair bond pair repulsions is much more as compared to the bond pair repulsions, so the angle is reduced to 115. Okay, this is 2 and 1. Please note this, sirs. AB3, this is 3 and 1 ammonia, had there been a bond pair in place of a lone pair, the shape would have been tetrahedral, but one lone pair is present, and due to the repulsion between the lone pair bond pair, which is more than bond pair repulsion, the angle is between bond pairs is reduced to 107 degrees from 105. So this value you need to remember. This is pyramidal shape, trigonal pyramidal. AB2E2, two bond pairs, two lone pairs. Bend shape. The shape should have been tetrahedral if there were all bond pairs, but two lone pairs are present, so the shape is distorted tetrahedral, or you say angular. The reason is lone pair repulsions is more than lone pair bond pair repulsions, which is more than bond pair bond repulsions. Thus, the angle is reduced to 104 point. So you need to remember this value. AB4E, here you see, four bond pairs, one lone pair. This is seesaw shape, as in A, the lone pair is present at axial position, so there are three lone pair bond pair repulsions at 90 degrees. In B, the lone pair is present in equatorial position, so that there are two lone pair bond pair repulsions, hence arrangement B is more stable. Got it now? When this is present here, it is with 90 degrees with all this, but when it is present here, it is 120 degrees with 2. So this is much better shape. So don't go with this, go with this. The shape shown in B is described as a distorted tetrahedron, a folded square, or seesaw. AB3E2, where three bond pairs, two lone pairs are there, this should be seesaw, T shape. In A, the lone pair are at equatorial position, and there are less lone pair bond pair repulsions as compared to others in which the lone pair are at axial position. So all the T shaped. See, it is better to keep the lone pairs. Very, very simple logic you see. When 5 electron pairs are there, that is odd number of electron pairs, lone pairs must be in the plane. Simple logic. If even number of electron pairs are there, like 6 electron pairs, lone pairs must be above and below the plane. Simple logic. Fine. So this is all about VSEPR theory, NCERT.